The present paper studies the inhomogeneous viscoelastic beam structure with 3 longitudinal circular cylindrical cracks shown in figure 1. The beam has a circular cross-section of radius R4. The length of the beam is L. The beam is clamped in its right-hand end. And the loading consists of an axial force and a bending moment applied at the free end of the beam. The cracks 1, 2, and 3 are circular cylindrical surfaces. The beam exhibits continuous material inhomogeneity in a radial direction. The material of the beam has non-linear viscoelastic behavior that is treated by using the stress-strain relation, formula number 1. The distribution of the material property B that is involved in this relation in radial direction is expressed by formula number 2. The longitudinal fracture of the beam is analyzed in terms of the strain energy release rate by considering the balance of the energy by formula number 3. After some mathematical transformations, one obtains formula number 5 for the strain energy release rate. The longitudinal displacement and the angle of rotation of the free end of the beam are obtained by applying formulas number 6 and 7. The strain and the curvature are obtained from equations number 8. The distributions of strains are found by formulas number 9. The stresses are found by substituting of strains in equation number 1. Then by substituting of formulas 1, 2, and 9 in formula 8, one obtains equations 10 and 11. The strain and the curvature are obtained from equations number 13 and 14. Finally, the strain and the curvature of the uncracked beam portion are obtained by using equations number 16 and 17. The strain energy that is involved of the solution for the strain energy release rate, the strain energy is found by using equations number 18 and 19. By integrating of stress-strain relation, this is formula number 1, the strain energy density in crack arm 1 is obtained by formula number 20. The strain energy is expressed by formulas 21, 22, and 23. Then, by substituting of strain energies in formula number 5, one derives formula number 24 for calculation of the strain energy release rate. The strain energy release rate is derived also by using formula number 25 for control of the solution. The complementary strain energy density is found by using formulas number 26 and 27. Then, by substituting of the complementary strain energy in expression 25, one obtains formulas 28, 29, and 30 for calculation of the strain energy release rate. The solutions derived are used to evaluate the influence of various factors on the strain energy release rate. For this purpose, calculations of the strain energy release rate are performed. First, the influence of material inhomogeneity is illustrated in figure number 2. It can be observed in figure number 2 that the strain energy release rate decreases with increasing of the parameter Q. In order to evaluate the effect of the location of crack 1 in radial direction, the strain energy release rate is plotted against R1 to R4 ratio in figure number 3. Figure number 3. One can observe in this figure that the strain energy release rate decreases with increasing of R1 to R4 ratio. The curves in figure 3 indicate also that the material nonlinearity leads to increase of the strain energy release rate. It can be observed in figure number 4 that the strain energy release rate decreases with increasing of the value of the parameter h. Increase of the radius R4 leads also to decrease of the strain energy release rate. The influence of material property P is analyzed too. For this purpose, the strain energy release rate is plotted against M to F ratio in figure 5 at 3 values of P. One can observe in figure 5 that the strain energy release rate decreases with increasing of P. In conclusion, it should be mentioned also that the analysis described in the present paper can be easily applied for beam configurations with more than 3 longitudinal circular cylindrical cracks. Thank you for your attention.